Hi everyone, today a video in the Equilibria series looking at Kp and partial pressures. So in the previous two videos of this series we've been looking at equilibria, reversible reactions that occur in solution, and we looked at how we can derive an equilibrium constant, Kc, in the expression for that. Remembering that Kc expression was the concentration of products divided by the concentration of reactants, all raised to their stoichiometric coefficients. However, many reversible reactions also take place in the gas phase, and gaseous equilibria also follow the equilibrium law, but their concentrations are often expressed in an alternative way using partial pressures. You can imagine that's a much more sort of logical way to do this, to express it as a pressure rather than as a concentration for a gaseous species. Now, if we have a mixture of gases, each gas will contribute to the total pressure. If I just have one single gas, the pressure is the pressure of that gas. But if I have a mixture of gases, well, each gas will individually contribute to the total pressure. The total pressure is simply just a sum of the individual pressures. And this individual contribution to the total pressure is called the partial pressure of the gas, P. Now, the partial pressure is the pressure a gas would exert if it occupied the same volume as the mixture and at the same temperature, but on its own. So if I have a mixture of gases A, B and C, they each have their own individual pressure, that's their partial pressure, lowercase p. And they also have a contribution. They will, if you add them all together, this produces the total pressure, the capital P. And so, for example, if I have gas A, that will be exerting a certain pressure in that total pressure. But the partial pressure of it is if I imagine I got rid of gases B and C, but I kept the same total volume and temperature of the system, that partial pressure would be the pressure that gas A exerted if it occupied that volume on its own. And the sum of the partial pressures is the total pressure. Now, mathematically, the partial pressure of a gas in a mixture is given by its mole fraction multiplied by the total pressure. So we can simply write an expression to say that the partial pressure of gas A, for example, Pa, is the mole fraction of A, and we give the mole fraction the symbol gamma, looks like a Y, and we multiply that by the total pressure, which is capital P. Now, what is the mole fraction? The mole fraction is simply the moles of that particular gas divided by the total number of moles in solution. So it's kind of akin to partial pressure. There'll be a total number of moles that we have in our solution for gases A, B and C, but specifically the moles of A, that will be our mole fraction. So the moles of A divided by the total number of moles in the mixture. Obviously this will be a number that's less than 1. So the partial pressure is the mole fraction multiplied by the total pressure. So we can calculate an equilibrium constant in the same way as we did for solution equilibria. This idea we have concentration of products divided by concentration of reactants. But it's now given the symbol Kp. And the way that I kind of remember it is that Kc is solution. Equilibria, we're using concentrations, so it's Kc. For these equilibria that go on in the gas phase, we're using partial pressures, and so Kp, P for pressure, Kp. But the expression looks exactly the same. Essentially, this time we've just got partial pressures, so it's the partial pressure. If we have a reaction of A plus B goes to C plus D, we have our partial pressure of C raised to the stoichiometric coefficient of C times the partial pressure of D raised to the power of D over the partial pressure of A raised to the power of A times the partial pressure of B to the power of B. So it's still partial pressure of products over partial pressure of reactants, all raised to their stoichiometric coefficients. So an example could be to calculate Kp for the gaseous reaction we have here. Hydrogen reacting with iodine to make hydrogen iodide. This is a completely gas phase reaction. We can write our expression for Kp. We do our products over our reactants. And so we have our partial pressure of the hydrogen iodide, the product on the top. And then we have our partial pressure of the hydrogen and the partial pressure of the iodine. Now, we're told in the question that it's 450 degrees Celsius, 3 atmosphere pressures. And we're told that we have 0.3 moles of hydrogen, 0.4 moles of iodine, and 1.4 moles of the hydrogen iodide when we're at equilibrium. So, to use that Kp expression, we have to essentially, when we used Kc, we converted our moles into concentrations and put them into the expression. For Kp, we have to use our moles here to work out mole fractions and then to work out partial pressures and put those into the equation. So the total moles, if we calculate the total moles, we have our 0.3 plus the 0.4 plus the 1.4. This gives us a total mole value of 2.1. So then remember, our mole fraction was the amount of moles of a particular species divided by the total moles. So the mole fraction for the hydrogen would be the 0.3 we have of that divided by 2.1. That's 1/7. The mole fraction for the iodine is 0.4 divided by 2.1, which is 4/21. And our mole fraction for the HI is 1.4 divided by 2.1, which is 2/3. Now you could write these down as decimals. I tend to keep them as fractions just because they're a bit neater to write. Now you also notice in the Kp expression that I've used curved brackets here and not square brackets. That's because we're not dealing with concentration, but with partial pressures. Now rather than writing a P with the sort of subscript of HI, I find it a bit neater just to draw it as curved brackets. But double check with your exam board exactly how they want you to write this in the exam. The key thing is that you don't write it as a square brackets because that denotes concentration and we're dealing with partial pressures. So we've worked out our mole fractions by doing the mole of the individual species divided by the total moles. We now need to work out our partial pressures, and the partial pressure is the total pressure multiplied by the mole fraction. Now the total pressure here is atmospheres. We're in atmospheres, so we have 3 atmospheres of pressure, and so our partial pressure simply is the 3 atmospheres times the 1/7 mole fraction of hydrogen. So the partial pressure of the hydrogen comes out to be 3/7 atmospheres. The partial pressure of the iodine is the total pressure, 3 atmospheres, multiplied by the mole fraction of 4/21. That comes to 4/7 of an atmosphere. And then finally, the partial pressure of the HI is the mole fraction of 2/3 multiplied by the total pressure of 3 atmospheres to give 2 atmospheres. And a way to just double check this is that the sum of the partial pressures should equal the total pressure. So if we do 3/7 plus 4/7 plus 2, that equals 3, which is our total pressure. So a good way to double check you've done these calculations right is to make sure that your partial pressures equal the total pressure. If they don't, then you must have made a mistake either in calculating the partial pressures or in calculating the mole fractions. Now that we have our expression, our Kp expression, we also have our partial pressures. We can simply put these partial pressures into the Kp expression. When we do that, we have 2 squared divided by 3/7 multiplied by 4/7. Remember, it's the partial pressure of the product divided by the partial pressure of the reactants. And when we do that, we end up with an answer of 16.3 for Kp. Now, like when we had our Kc expression, we had to work out the units for Kc. And we did this by simply looking at our Kc expression, looking at how many concentrations we had on the top, how many concentrations we had at the bottom, working out how many mole per decimeter cubed units that was, and then cancelling out. We can do the same thing with Kp. Here we were given everything in atmospheres, so we have essentially atmospheres squared on the top, and then we have 2 lots of atmospheres on the bottom. That's the same again as atmospheres squared. And so because we have the same on the top and the bottom, they cancel out to give Kp as a unitless number here, just 16.3. But we still have to always make sure that we work out our unit. So the Le Chatelier's principle that we've been talking about and using in the past 2 videos of this series for solution equilibria works in exactly the same way as it did for solution equilibria as it does in these gas phase equilibria. The only difference being that we've replaced our concentrations by partial pressures. But the actual way that the Le Chatelier's principle works and all of the equilibria laws that we've looked at work are exactly the same. Remember that the Chatelier's principle tells us that if we disturb an equilibrium, if we change an equilibrium, somehow change a condition, that the equilibria will shift in the direction to oppose that change. So for example, if we have a reaction, a gas phase reaction that is exothermic in the forward direction, that means it's a negative enthalpy change, we're giving out heat. If I increase the temperature due to the Chatelier's principle, the equilibrium will shift in the direction to oppose that change. To oppose the change of increasing temperature would be to reduce the temperature, to take heat in. That's the endothermic direction, which is the reverse direction back to the reactants to the left, and so heat is absorbed. By doing this, we produce more reactants, and hence if we write out our Kp expression, like when we looked at Kc and how the number of that can change, if we have increased our temperature for this exothermic reaction, well, the equilibrium shifts left, we make more reactants, therefore the bottom line of our Kp expression becomes greater, and we decrease our Kp number. If we have a pressure change, as we've seen before in some of the other reactions that we talked about for a Kc, but really should have been labelled as a Kp reaction in the previous videos, if we increase the pressure, it forces to the equilibrium in the side with the fewest molecules of gas. This is just the Chateau Principle again. It wants to oppose that increase in pressure, so it moves to the side with the fewest molecules on, and so that will reduce the pressure. Changing the pressure, remember, only affects the equilibrium position when we have different numbers of molecules on either side of the reaction. If we have a reaction that has 2 molecules of reactants, 2 molecules of products, then that means that a pressure change is not going to affect that equilibrium position. Now, increasing the pressure will increase of a gas phase reaction will increase the rate of attainment of equilibrium. Same way that if we increase the concentration of a solution phase equilibrium, that will increase how quickly we get to the equilibrium position, because we're now putting more molecules into a given volume, essentially. And therefore the collisions are much more likely. Increasing the temperature also has exactly the same effect, because we're now going to, a lot more molecules are going to have energy greater than the activation energy, and therefore more successful collisions. And remember that a catalyst does not affect the position of equilibrium and hence the value of Kp, but it increases the rate at which equilibrium is reached, because it affects the rate of both the forward and the backward reactions equally. And so therefore overall there's no net change to the position of the equilibrium, but the attainment of equilibrium is quicker because our activation energies have been reduced. So, time to have a go at a question, just one question this time, with this Kp calculation, this gas phase reaction. So we have to calculate Kp and include any units. So if you'd like to have a go, pause the video and the answers will be on the next slide. So our reaction is phosphorus pentachloride, PCl5, dissociating into phosphorus trichloride, PCl3, and chlorine. Now this is a completely gas phase reaction. And so we have this equilibrium of our equilibrium arrow, our reversible arrow, that's sort of 2 half arrows going in opposite directions. And we were told that our pressure was 12 atmospheres. And we were told that the amount of each gas present at equilibrium was 0.4 moles of the PCl5, 0.7 moles of PCl3, and 0.9 moles of the chlorine. So remember, the first thing we need to do, because we need to use partial pressures, to calculate partial pressures, we need to have a mole fraction. So we need to calculate our mole fraction first. Remember that the mole fraction was simply the moles of a particular species divided by the total moles in that reaction. So we calculate our total moles. 0.4 plus 0.75 plus 0.9 gives us a total moles of 2.05. And so our mole fractions are simply those individual mole components divided by 2.05. So the mole fraction for the PCl5 is the 0.4 divided by 2.05. Again, I'm going to write these as fractions just to keep the numbers a bit neater. That comes out to be 8/41. Our mole fraction for the PCl3 is 0.75 divided by 2.05. That comes out as 15 divided by 41. And our mole fraction for the chlorine is the 0.9 moles of it divided by the total, 2.05, to give 18/41. Now we then consider our partial pressures. So remember that to calculate the partial pressure, we have to take the total pressure and times it by the mole fraction. Now our partial pressures here will be in atmospheres, because our total pressure is in atmospheres. Make sure the units always match. And so the partial pressure for our PCl5 is the total pressure, 12 atmospheres, multiplied by the mole fraction of it, which is 8/41. And that comes out to be 96/41 as a fraction. So that's 96/41 atmospheres. If we did the same things for the PCl3, we take our total pressure, 12, multiplied by the mole fraction, that comes out to be 180/41 atmospheres. And finally for the chlorine, we do our mole fraction, 18/41, multiplied by the total pressure of 12 atmospheres, to give 216 over 41 atmospheres. Now again, you could just double check by adding together those partial pressures, and if you do that, if you add together all those partial pressures, you'll see that the total pressure comes out to be 12. So it's a good way to just double check that you've done your calculation. Does the sum of the partial pressures equal the pressure? Then we can write our Kp expression. So remember that Kp is the partial pressures of the products divided by the partial pressures of the reactants, all raised to their stoichiometric coefficients. And so here, our expression for Kp is the partial pressure of PCl3 multiplied by the partial pressure of Cl2 over the partial pressure of PCl5. And again, I'm using sort of rounder brackets to indicate that it's a pressure. I'm not going to write it as P and then the sort of subscript for what the species is. The key thing is to make sure that you don't use square brackets, because this is a partial pressure calculation and not a concentration calculation. And so then we just have to put our partial pressures in that we worked out earlier. And when you put these numbers in, you end up with an answer of 9.9. We then have to work out our units, remember. Now in this case, we were given our pressure in atmospheres. So all of the pressures that we deal with in the Kp will also be in atmospheres. So on the top, we have 2 lots of the atmospheres, same as atmospheres squared. On the bottom, we just have the 1 species, so it's just atmospheres. So cancelling out the atmospheres from the bottom and the top just leaves an atmosphere on the top, and therefore our unit is atmospheres. And so our answer for Kp is 9.9 atmospheres. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on my tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to email me. I'll be happy to help.